Powering the future. Choosing the right AI for virtual power plants. Introduction. The power industry is experiencing a major shift with the rise of distributed energy resources, so-called DERs. A key future player in this transformation is the virtual power plant, also called a VPP. This network combines DERs, including solar, batteries, electric vehicles, and heat pumps, to act like a single large power plant. It will also integrate residential, commercial, and industrial loads over time. VPPs are becoming essential for managing modern energy systems and deep decarbonization. While VPP adoption has grown steadily over the past decade, it remains below its potential. This can be attributed to the novelty of the concept, regulation, size, and the complexity of managing a vast portfolio of different technologies and individual assets. As VPPs become more established, exploring the use of artificial intelligence for optimization could be a game changer. Why consider advanced optimization techniques for VPPs? Managing the diverse assets and loads of a VPP in real time poses significant challenges, and there are several factors supporting the usage of AI. Resource coordination and aggregation. DER resources need to be efficiently coordinated and aggregated to maximize their collective impact. Optimization algorithms ensure that DERs work together seamlessly, responding to grid conditions and energy demand in real time. Energy management. VPPs must balance energy supply and demand across diverse resources. This involves optimizing the dispatch of energy from various DERs. Advanced techniques consider factors like resource availability, load profiles, and grid constraints to minimize costs and enhance reliability. Market participation. VPPs participate in electricity markets, selling surplus energy or providing ancillary services. Effective participation requires strategic decision-making. Optimization models help VPPs determine optimal bidding strategies, considering market prices, demand fluctuations, and regulatory requirements. Resource uncertainty. DERs are inherently uncertain due to factors like weather conditions, EV charging patterns, and battery degradation. Advanced optimization accounts for this uncertainty, adapting resource schedules dynamically. Control and communication challenges. Managing a diverse set of DERs involves control and communication complexities. Optimization techniques address issues related to data exchange, latency, and synchronization. In summary, advanced optimization techniques empower VPPs to operate efficiently, adapt to changing conditions, and contribute to a more sustainable energy future. AI approaches for virtual power plants. Which AI approach is relevant for VPPs? A short overview of the key techniques at hand. Supervised learning involves training a model using labeled data, where each input is associated with a correct output. In supervised learning, the model learns to map inputs to predefined outputs based on the provided labels. One example for using supervised learning in a VPP is power flow optimization. Unsupervised learning deals with unlabeled data, aiming to discover patterns or structures within the data. Clustering and dimensionality reduction are common tasks in unsupervised learning. Unlike supervised learning, there are no explicit output labels to guide the learning process. One example is again power flow optimization. Deep learning uses neural networks with multiple layers. It excels at tasks like image recognition, natural language processing, and speech synthesis. Deep learning models learn hierarchical representations from raw data and typically are trained using large amounts of labeled or unlabeled data. Reinforcement learning is an agent-based approach and is distinct for VPPs in several ways. Sequential decision-making, reinforcement learning involves making a series of decisions over time, where each action affects subsequent states. Trial and error. Instead of relying on labeled data, so-called agents learn through trial and error. They explore the environment, receive rewards or penalties, and adjust their behavior accordingly. Data is not part of the input, but collected through trial and error. Through trial and error, the agent interacts with the VPP environment by making decisions, for example, dispatching power or charging batteries. It observes the resulting rewards and learns to choose actions that maximize the long-term reward. maximizing cumulative reward. The goal is to learn optimal behavior to maximize cumulative rewards over time. Interactivity. Unlike supervised learning, reinforcement learning interacts with the environment, gathering data as it goes. Reinforcement learning is an iterative cycle of exploration, feedback, and improvement. In summary, while supervised and unsupervised learning operate on existing datasets, reinforcement learning actively explores and learns from its environment, making it well suited for dynamic decision-making and complex control tasks such as VPPs and their optimization. Reinforcement learning for virtual power plants. Let's have a brief look how a reinforcement learning system is structured. This helps to understand better the way it can work in a VPP context. There are two main characters in reinforcement learning: the agent and the environment. The agent is the decision maker or learner. It interacts with the environment. The environment encompasses everything outside the agent that the agent interacts with. The VPP environment consists of the DERs connected to it, such as solar panels, wind turbines, and battery storage units. These provide data on their current power generation, storage levels, and operational constraints. The agent resides within the VPP control system. It receives data from the environment about the current state, for example, total power generation, demand forecast, or electricity prices, and decides on actions to optimize the performance. There are additional components within the system, and some of them are as follows. Reward. The environment provides immediate feedback to the agent in the form of rewards or penalties based on its actions. The reward function is designed to incentivize the agent to make decisions that align with the goals. These goals can include 1. Maximizing profit, selling electricity to the grid at peak prices and buying when prices are low. 2. Maintaining grid stability, responding to fluctuations in demand by adjusting power output from DERs. 3. Minimizing operational costs, optimizing energy use within the VPP to reduce reliance on expensive sources. Based on the chosen reward function, the agent receives positive rewards for actions that achieve these goals and negative rewards for actions that don't. State. A state represents the complete description of the world at a given moment. It includes all relevant information. Action. Actions are the choices the agent can make. They influence the environment. Return. The cumulative reward over time, which the agent aims to maximize. The agent's objective is to learn behaviors that maximize its cumulative reward. Reinforcement learning formalizes the idea that rewarding or punishing an agent shapes its future behavior. Policy. The policy defines how the agent behaves at a given time.